This video is going to be a walkthrough of some typical exam style questions you get on the topic of quantum physics. So we're going to look at photoelectric effect, we're going to look at some to do with electron transitions and emission spectra, and we're also going to have a look at some sort of random ones that kind of incorporate lots of different parts of quantum physics. So we're going to look at a couple of multiple choice questions first. I'll talk you through each one and use the timestamps at the bottom to find a question which you might be on a topic that you might have struggled with. So in this question here, we've got light of a certain frequency greater than the threshold frequency of a metal is directed at a metal. Photoelectrons are emitted from the surface. The power of the light incident on the metal surface is doubled. Which row shows the effect on kinetic energy and the effect on the number of electrons or photoelectrons emitted each second? So to understand this question, we need to be really clear what affects the photoelectric effect and the energy the electrons are given and the amount of them per second. So hopefully we know for the photoelectric effect to happen, it is all to do with the energy of the incident photons and also to do with their frequency. It's not to do with how many there are. But once you go above a threshold frequency, if you increase the power, that is essentially the same thing as increasing the intensity of the light or intensity of the infrared radiation that is incident onto the surface. So if you're increasing the intensity is basically the number of photons per second. So the amount that are hitting it in a certain time will increase. So in that case, if I've got multiple photons coming in, essentially I can, let's say I have two photons coming in, I can have two electrons being emitted, three photons, three electrons being emitted. It doesn't change their energy, it just changes whether they're emitted or not. So it's either one of these two to start to answer the question. It doesn't affect the kinetic energy, but it might affect the number of photoelectrons. So because it says it's doubles, it makes more be emitted per second. So actually this one is doubled as well. So the correct row is row C for this question. On to the next question on the side here, we've got a graph of maximum kinetic energy of these photoelectrons and the frequency of incident radiation. And the question says, which graph shows the results for a metal Y that has a higher work function than X? Now you might notice on this graph there's nothing to do with work function, we've got to be able to figure out ourselves. So using the kinetic energy equation, which is in your data sheet, HF equals work function phi plus EK max, and we can sort of figure out, well actually when EK max is 0, so when they're just about being emitted, then essentially the H times the frequency is equal to the work function. So basically we've got to try and find the point which has from this graph what each part of the graph represents. Let's grab the last bit. So the part of the graph where there's no kinetic energy is this bit here, so where it crosses the x-axis. So essentially when it crosses over to this axis here, at this point that's called the minimum or the threshold frequency. Okay, so the frequency at which the electrons are just being emitted, which corresponds to the work function. So we're looking for Y has a higher work function. We're looking for a part where the Y will cross the x-axis, a bit confusing all the x's, isn't it? A little bit higher up. So let's look at which one that might be. It could be A, it can't be B because that's got a lower threshold frequency. It couldn't be C because that doesn't happen either. And actually it couldn't be D either. So we're left with the fact that it's A in this question. There's another clue as well, which is actually if you know what the gradient of this graph represents, it represents Planck's constant. Now, Planck's constant is a constant, so that's not going to change. It's just going to be the intercept here that changes for this question. Another multiple choice question about the photoelectric effect. Here we've got a beam of light of wavelength lambda is incident on a metal surface. Photoelectrons are emitted. The wavelength of the light is halved, but the energy energy incident per second, or the intensity, is kept the same. So which row in the table is correct? So this time we've got the intensity stays the same, but if we consider the photons coming in, they now have, if you were to rewrite the equation E equals HF, we can rewrite it as E equals HC over lambda. So if the lambda is decreased or halved, then the energy is going to be increased. So they're coming with more energy, so therefore they're going to give more of that kinetic energy to the photoelectrons. So if we look at the options we've got here, has to be one of the ones that results in it increasing. Now the number emitted per second, this is really important, doesn't depend on the wavelength. It only depends on the intensity. So the number of photoelectrons emitted per second actually doesn't change at all. So for that reason, it's going to be option A, because it's unchanged. Right, we've got a couple of extra ones here from the quantum physics topic. This one's all about using the de Broglie equation, de Broglie wavelength, the different particles. Now, this question is really interesting because there's only one number given to us. It looks like we are going to have to work out the speed using this equation, but we can actually use a little trick to use ratios. So the electrons moving in the beam have the same de Broglie wavelength as protons, moving at a speed of 2.8 times 10 to the power 4. What is the speed of the electrons? So we know what the mass of a proton and the mass of an electron is, so we could work out the wavelength for each and sort of go from there, but we could just look at the ratios between their different masses. So if we sort of say that's a constant, then what we can do is look at and the wavelength is a constant also, then what we can do is say, well, mv equals 1, so basically mass is inversely proportional to the velocity. So for questions like this, we can, depends how you want to do it in terms of ratios, but anything like this, if you've got a proportional relationship, you could say the sort of times these two things together. So the mass of the electron times by the velocity of the electron is constant. The two things are constant, so therefore it's equal to the mass of the proton times by the velocity of the proton. If you want to do the ratio of each, that also is totally fine. If you want to do the ratio of masses and ratio of velocities, doesn't really matter. But at that point, we're just plugging in our numbers. So mass of an electron, 9.11 times 10 to the minus 31, times by the velocity of the electron we don't know. That equals the mass of the proton, so 1.6. 7 times 10 to the minus 27. This is all from your data sheet, by the way, not from the given in the question, times by the velocity. So if we solve, once we've got those numbers in, if we solve for the velocity of the electron, so if we put all those in place, we get around about 5.13 times 10 to the power 7 meters per second, which leaves us with option D. So option D is our correct answer there. Okay, moving on to this question on the right hand side here, which questions like this can quite often confuse people. We've got some electron transitions here. So it says the diagram shows an energy level diagram for a hydrogen atom. Electrons with energy 13 electron volts collide with atoms of hydrogen in their ground state. What is the number of different wavelengths of electromagnetic radiation that could be emitted when the atoms de-excite? So there's a really common misconception here, which is to just work out 13 electron volts, see which transition could happen, and then sort of go from there. But we've got to be really careful. Let's talk about the atoms de-exciting. So if the electrons have enough energy, so 13 electron volts, we've got to figure out which of these are the electrons going to be promoted to or excited to in the first place. So they've got too much energy to go from here, too much energy for here. 13 electron volts means it could be somewhere between these two levels, but we know these energy levels are quantized, so it gets excited up to this point here. And there'll be a tiny bit of energy left over for this electron to sort of go on its way with. Now, once it's got to that point, we've got to figure out, so when it de-excites, which different routes it could take. So the most obvious route is it could go, starts off here, goes back down to the ground state. That would be one option. Second option is it could go down to level 1. Third option is it could go down to level 2. That's 3 options. Now, if these two are true, the second thing that happens, because it has to go down to the ground state eventually, because it's got to lose all its energy, is that once it gets there, because it then go down to the ground state, so between level 1 and the ground state, it could go between here and the ground state, so this bit here. Now the last option is once it goes from here to here, it could then take an extra step. It could go 1 to there, and it could go from level 2 to level 1 before then going back down to the ground. But we've already done that one already. So let's count these up then. So we've got 1 for this big one initially. We've got 2, 3 different energy transitions, 4, 5 down here, and there are 6 in total, which that electron could do as it de-excites. So the answer is option 6. We've got another multiple choice question here involving electron transitions. So some energy levels of a lithium atom this time are shown below. We've just got n equals 1 and n equals 2 and the ionization level. So a free electron with kinetic energy of 6 times 10 to the power minus 19 joules collides with a stationary lithium atom in this level here. The lithium atom is excited, so it goes up to this level here. What is the kinetic energy of the free electron after the collision. So not the electron that's been promoted. The electron that caused this all would be one that came in with an initial kinetic energy, is given up some of its energy to the electron to do that, and it's going to go on its way with how much energy. So if it had 6 times 10 to the power minus 19 to begin with, we've got to figure out how much is lost to sort of promote that electron to go from one level to another. Right, the next question we're going to look at is all to do with emission and absorption spectra. This is from the June 2022 A-level paper 1. So first bit is a bit of an interesting one. We've got a lot of information here, so let's just check what we've got. We've got helium was discovered by analysing the light in absorption spectrum of the sun. Figure 1 shows the position of the brightest lines, A to F, in the emission spectrum. The brightest lines also of sodium and hydrogen are shown here. Before helium was identified, some scientists suggested the lines of helium spectrum seen in the absorption spectrum of the sun were due to the presence of sodium and hydrogen. Discuss, with reference of lines A and lines F, A to F, the evidence for and against this suggestion. So it's kind of like a bit of problem solving thing, this one. So the idea is, originally scientists thought helium was a new element, but some scientists said, oh, maybe it's a version of hydrogen or sodium. So actually this one is a lot easier than people think. It wasn't that well answered in the actual paper, this one. But if we do sort of game of spot the difference, what we can notice is in helium we've got one line here that corresponds to hydrogen. So down here. So what we could say is that line A. So what we've got to have a look at is these different lines and try and figure out, well, which of them are in sodium and hydrogen. So line A caught people out because it looks like it might be in hydrogen, but it's not quite. It's not the same line. It's a little bit further along. Line C, however, if we look at this stage here, this line here, is exactly the same spot as helium as the hydrogen is. So what we'd say is you could say line C is in both the hydrogen and helium spectrums or spectra. So that's in both, indicates it could be like another version of hydrogen spectra. The next line we're going to have a look at, let's have a look at D. That's not got any comparison. Line E is the other one where we can hopefully see that in the sodium spectrum we've got a very, very similar line there. So what we'd say then is that something like line E is in both helium and sodium spectra, just like before. Then that's not the full thing here because it's about discuss, and we've got to reference all these lines. So we can talk about which ones are sort of missing from any of them. So we could say something like, well, if I look at line D, that's not in either one of these. So line D is missing from both sodium and the hydrogen spectra. Okay, over the page. Next we've got a calculation question. So we're trying to calculate in electron volts the change in energy level responsible for the spectral line labelled E. So I'm going to have to flick back a little bit to find E, so we can work something out. The only information we've got here, the only numerical information on this diagram, is the wavelength. So if you get yourself a ruler, just give you my calculator quickly here, and you've got to figure out what wavelength does E occur at. Now there's no grid lines here, there's a little bit of leniency with this one. I think the general consensus when my class did it was about 585 nanometers, or I think they allowed 580 to 590. So once we know that, what we can do then on the other page is say, well, the wavelength is 585 nanometers. So the change in energy level, we're after in electron volts. So the change in energy level is equal to HF, or is equal to HC over lambda in this case. So therefore energy is Planck's constant, so 6.63 times 10 to the minus 34 times by speed of light, so 3 times 10 to the 8, divide by the wavelength we just found in meters, so 585 times by 10 to the minus 19. Sorry, minus 9, beg your pardon. Once we've done that, we've got an answer in joules of 3.4 times 10 to the power minus 19. So that's 2 marks already, but finally we need to work out an electron volts. So if you don't know how to convert joules to electron volts, make sure you learn this now. So joules to electron volts, there are 1.6 times 10 to the power minus 19 joules in an electron volt. So we divide to get to electron volts. So that for us equals 2.125. And there was obviously a range with this answer because you're looking from the diagram from the previous page. So lastly with this question, and this is one that caught people out as well when they did this question, it's explained with references to processes within an atom, the difference between an emission spectrum and an absorption spectrum. Always with 3-mark questions like this, I would definitely use bullet points and sort of stagger your answers so you don't end up waffling. Let's talk about our emission spectrum first. So we'd say in an emission spectrum. So what happens is, in an emission spectrum, if I've got an atom here with a nucleus, photon comes in, emission spectrum, not absorption, there you go, photon doesn't come in. So in our emission spectrum, an electron goes from a higher to a lower energy level. So this is my low energy level here, and when it does that, it loses energy. Energy gets released in the form of a photon with energy equals to HF. So we'd say something like in an emission spectrum, an electron is de-excited, or you could say, and moves to a lower energy level. And as it does that, this is the really important bit, and then you say it emits energy in the form of a photon. Now, if you've got that word perfectly for emission spectrum, actually absorption spectrum is not too bad because it's kind of the same thing but in reverse. So for an absorption spectrum, what happens is you've kind of got the opposite. So a photon of light comes into the atom and that causes an electron to be excited. So to go up to another energy level. So we could say something like in an absorption spectrum, an electron absorbs or takes in energy from the photon or from a photon and is excited to a higher energy level. So the marks in this question are for describing the processes correctly. So describing the excitation for absorption and de-excitation for emission. Also wants you clearly saying that the energy gets provided by the photon or emitted in the form of a photon. So that's what the extra mark is for there. Now a lot of people, you don't need to actually talk about the spectrum itself, it just says the processes within the atom. So that is absolutely fine enough here for 3 marks. The last question we're going to go through is a tricky one. It's all about something called, quite commonly called a photocell or a vacuum photocell, which is an application or example of the photoelectric effect. So we've got this circuit here. We've got an electrode, we've got a photoemittive surface, meaning photoelectric effect is going to happen there, and a potential difference, monitoring the voltage being supplied by a variable voltage supply. So our current is measured on the microammeter only when electromagnetic radiation with a frequency greater than a certain value is incident on the surface. So imagine our photons going in here and the electrons are going to cross this gap and get to the other side, then go around the circuit and be measured by the ammeter, the microammeter. So the first question is to explain why the frequency of the EM radiation must be greater than a certain value. So other parts of this question are quite tricky. This one should be relatively straightforward. So why must the frequency be greater than like a threshold frequency? So the idea is that there is a minimum energy needed to overcome what's called the work function inside the metal. So we could say something like there is a minimum energy needed to remove or liberate electrons from the metal. You don't need work function for this mark, but I'm going to put it in anyway. So it's called the work function. Now, how do we relate frequency to energy? It's not enough just to quote the equation, but we'd say that the energy of a photon depends on its frequency. So you'd say something like, well, that's E equals HF. Moving on to the second part of the question, we've got a graph here which it says use the apparatus with a monochromatic, so all one colour, all one wavelength, one frequency, light source of constant intensity. Measurements are made to investigate how the current varies with positive and negative values of the PD of the supply. So this question, if you want to look in like your revision notes or whatever, which bit to revise, it's all to do with this thing called stopping potential, which will come later in the question as well. The idea is if I apply a potential difference, depending on whether I apply it, positive, negative, or negative, positive, that will either try and slow down the electrons or it will speed them up. Now I'm hoping we can see from this graph here with the current in the y-axis that it's with a positive potential difference, that's actually the one that's speeding them up. That's why the current is constant there and goes down to 0 on this side. So that's going to be a bit important later. Now for the number of photoelectrons it's asking for here, it says when the current is a maximum. So when the current is a maximum, that's at 30 microamps. So at 30 microamps, we should know, so current is change in charge over change in time, or rate of change of, rate of flow of charge. So we're trying to find the number of photoelectrons. So the current we can then say is the number of electrons times by the charge on each electron, 1.6 times 10 to the minus 19. Now because it's per second, this becomes 1. So to find the number of photoelectrons, what we've got to do is then say n equals the current divided by E, which E is 1.6 times 10 to the power minus 19, and current we just said is 30 microamps, so 10 to the power minus 6. So if you divide those two numbers, we should find it comes out to 1.8 something around, so 1.9 times 10 to the 14 electrons leaving that surface every single second. Right, next question refers back to what we were talking about a second ago with the stopping potential. So it says, explain why I reached a constant value for positive values of potential difference. So on our graph, you can see it levels off here. So that must mean essentially what's happening is the current reaches a maximum because all the electrons are being emitted from the surface that could possibly be emitted. Because it's a monochromatic light source, you cannot, and it's a constant intensity, you cannot increase that to get more electrons out. With that intensity and that frequency, there's only a maximum amount that can be emitted from the surface. So how do you put that into an answer? So it goes something like this. So you'd say the number of electrons emitted from the surface, or each second from the surface, depends on the intensity. So it depends on the intensity. So that's the number of them. Don't forget their energy depends on their frequency or wavelength, but this depends on the intensity of the EM radiation. And we can say, well, this the question says this is constant, so that's not changing. Next point is to say, well, as soon as the current reaches maximum, that means that all the electrons get from one side to another. So that means that when we say the current or constant current is reached when all the electrons emitted reach the other side, or reach this part of the diagram is called the anode. So they get from here to that part, you could say electrode there if you wanted to. That's the positive plate. Next is why, sort of related to this, why does I decrease as the value of V becomes negative? So if you imagine here, we're supplying a potential difference. If I were to flip around the terminals, so this time I've got a negative here and positive here. So what would happen is if I'm applying a potential difference across this end and this end, if I've got a negative potential there, what it means is the electrons are going through towards the electrode. There's going to be a point at which they're going to stop still because they're experiencing this negative potential from the electrode because we flipped around the voltage. So when that happens, that's sometimes known as the stopping potential, and that means that actually some of them are going to end up stopping. Some of them don't have high enough kinetic energies. So we're going to start off with that with our explanation. So we'd say something like when the PD is negative, the electrons lose kinetic energy. When crossing the gap, you can say they stop still. Losing speed would probably be fine here, but I'd definitely use kinetic energy when crossing the gap. Now, what's really important to note is that it doesn't happen to all of them at the same time, because electrons that get emitted from here have a range of kinetic energies. You might remember from the equation HF equals work function plus EK max. That's the maximum. They don't all have that kinetic energy. Some of them will have less, some will have more, depending on where they are in the surface, if they're deep down or close to the surface or not. So what we'd say then basically is that the electrons have a range of kinetic energies from the surface of the surface that's emitting them. So what that means is that if they're all crossing over, essentially, so as V is more negative or has greater negative values, V is more, I can't write here, is more negative, fewer. So just says decreases, doesn't say why it's go to 0, but it decreases because fewer electrons have enough energy or kinetic energy to reach the anode, because there's that potential difference trying to stop them. So some of them will get there, some of them won't. By the time we get to here, obviously none of them get there, but at these points here, some of them are getting there, some of them are not, basically. Lastly for this question, it says it's repeated with a different material, different surface, that has a smaller value of the work function. So work function has gone down. Everything else is unchanged, the EM radiation, etc. It says discuss the effect this change in the surface has on the value of the stopping potential. So we can use a couple of equations to help us here, because they're really useful. You don't get marks for quoting them, but you do get marks for using them correctly. So the photoelectric equation, first of all, so HF equals the work function plus EK max. So even though we don't have to discuss stopping potential till right at the end, because we do get marks here for discussing what happens with a lower work function. So if everything else is changing, I'm going to rearrange this for our kinetic energy. So kinetic energy EK max equals our HF minus the work function. So what we'd say first of all, we could say something like if the kinetic energy is equal to HF minus the work function, then if HF isn't changing, so if HF, so I should probably say energy of the photon is unchanged, a lower work function, so that's phi, means lower kinetic energy. So if the energy of the photon is unchanged, a lower work function, because you're subtracting it from here, will mean a higher kinetic energy of the electrons. Okay, so that's relationship 1. So let's try and relate that to stopping potential then. So kinetic energy, if you're imagining particles with a kinetic energy being emitted from the surface and they're going from one end to another, if I was to apply a potential difference across them, with a negative potential here, positive potential here, if I increase this enough, they'll stop in their tracks, and all their kinetic energy will be transferred to potential energy. Now for a electric field, which you're applying here basically, so in this case that would go in that direction, the equation for that is equal to the charge, so work done equals charge times PD. In this case it's the charge on an electron times by potential difference. So what we'd say then, in that case, let's link this to kinetic energy. If you've got a higher kinetic energy, you have a higher stopping potential. So you could do that with the equation, always useful to do. That's the relationship the mark scheme's looking for here. For the final mark, I realised I actually should have included one extra thing, which is if we're talking about the maximum kinetic energy, then you do get marks. Underline the mark scheme here, you've got to talk about maximum kinetic energy throughout. So what you're talking about, those particles. Alternative way of doing this question, so it's one for saying the maximum kinetic energy and one for this last statement here. The alternative is, if you wanted to, you could do HF equals the work function plus EK max. You could change this, as we just said, into EV, so so that should be plus EV, with V being the stopping potential. If you rearrange this, you can sort of get those relationships out of our equation like that. So you've got to mention them, but that's an alternative way of doing it. So we found those useful. Some of them can be really tricky about quantum physics, some of them a little bit easier. And do make sure you like the video and give me a comment on any of the topics you want me to do some exam questions of.